Welcome to our introduction to the lab for the week of October 12th, and this is part 2. We're going to talk about doing exercise 21, measuring the diameters of Pluto and Charon. And so what you want to do here, what's important here, let's start with that, is that as seen from Earth, the orbital plane of Charon and Pluto around one another, which we would now think of this as a binary Kuiper belt object. Actually, it's multiple because there are multiple objects in that system, not just Pluto and Charon. What you would see is that the orbital plane is tilted such that every once in a while, one of these objects passes in front of the other and blocks light from it. So you'll see, if you see both objects, then one object, then both objects, then one object. You see brighter, dimmer, brighter, dimmer. And we will talk about this again later in the course when we're talking about eclipsing binary stars. This is one way we can measure radii of stars, the way we're measuring the radius of Pluto in this lab, for example. We could use to measure the radius of a star by watching two stars who have their orbit, they're orbiting each other, and they have their orbital plane tilted such that we see one of them passing between us and the object and blocking out the light, and we can see that. Now, if you have a smaller object passing in front of or behind a bigger object, you have these two objects like this. Then we move across here, and we see that at this point, when the objects look like this, we call that first contact. And at first contact, you start to lose light. And you will lose light until you reach second contact right there. Doesn't matter if this is in front or behind. If it's behind, you're blocking light from the smaller object. If it's in front, you're blocking an equal area of light from the bigger object. It might not be an equal amount of light, but it's an equal area of light. If the two objects aren't the same brightness, then you could be blocking more light when one of them's in front of the other one, and then vice versa. But at this point, it will move across here. That's second contact. And it will move across the face of this object or behind this object, and you'll have a steady amount of light that's being lost until you get to this point over here, and that's third contact. And at third contact, you start to move back to full brightness, and at fourth contact, you have full brightness. So an idealized light curve, it's a brightness versus time graph. That's what a light curve is. And we'll talk about light curves on and off throughout the term here. So you'll hear us talking about them again. But an idealized light curve would look something like this. First contact, second contact, third contact, and fourth contact. Okay? Full brightness, light starts to go away. All the light that's going to go away is gone. It's flat. And then it starts to get brighter again. And then you're at full brightness again. So make sure that makes sense to you and you see that going on right here. And this is what you're going to plot for the Pluto-Charon system. You have the data, just like in exercise 18. You have the data given to you in a table. And you have graph paper provided for you. I don't care if you use this graph paper. I don't care if you make your graph electronically. I don't care how you go about doing this. But you've got the graph paper provided for you. We're measuring brightness in something called magnitudes. So we're talking about the change in magnitudes. And we haven't yet introduced the magnitude system for brightness measurement. And we won't until we go back and do chapter 3. And so we're not going to introduce, actually, we may not do it until a little bit later than that. So anyway, we'll introduce the magnitude system later on for brightnesses. I'll think about whether we want to kick it in this week just to talk about it. But that's down the road. Don't worry about what that is. It's just a way to measure how bright the system is. And so when one of these objects passes in front of the other, you see the system get dimmer, and you can draw this on here. So what you want to do, this is a noisy system. It's very hard measurements to make. And so you're at the threshold of being able to detect this. And if you're at the threshold of being able to detect this, then you've got you're going to see a lot of noise in the system. So instead of looking like this, it's going to look like your graph is going to look something like this. So my recommendation is to fit a line to the different segments of the graph. And you can do this by hand with a ruler. Right on here, you can draw a best fit line. That's great. And then draw a line right here. And where those cross, that's second contact. And you draw a line right there. And where those cross, that's third contact. And you draw a line right there, and that's fourth contact. And you draw a line right there, and that's first contact. So you can measure the time of first contact, second contact, third contact, and fourth contact that way. And that's all great. So that's what I recommend that you do. And see if you can find the times of those. If you're doing this in Excel or something like Excel, Excel will fit the lines to those different segments for you, and you can calculate where those lines cross if you want to, and you can see that, but it's fine just to do it by eye. And then what you know is we use this idea that the distance traveled is the velocity times time to say that okay, if we know the velocity, and the lab works you through this to say, okay, how we know the circumference of orbit, and if we know the circumference of orbit, we'll use that, and the time of orbit, the period of orbit for the Pluto-Charon system, we'll use that to calculate the relative velocity of the two systems, how fast they're moving relative to each other there. And so once we do that, we have the velocity of the system, then we can use the time between contact to determine the distance traveled between contacts. But this is interesting to us because going from, remember, first contact is this and second contact is this. So the distance traveled between first and second contact is just the diameter of the smaller object. Everybody see that? You see you've moved from one side of the smaller object being in contact with the left side of the larger object to the other side being in contact with the left side of the larger object. So you've moved one smaller object diameter. So the diameter to go from first contact to second contact is going to be, this distance is going to be the diameter of the smaller object. Going from third contact to fourth contact is going to give you the same thing. So there's redundancy in the system. Going from there to there is going to give you the diameter of the smaller object. So you have two ways, by calculating this time and calculating this time, you have two ways to determine the diameter of the smaller object in this system, and the lab walks you through doing that. And you can average the result of those two things when you're done. So find your time from here to here, get your diameter, find your time from here to here, and get your diameter, and average those things when you're done. Right there. Now, going from 1 to 3 or 2 to 4, so if we go from 1 to 3, we see that the smaller object has gone from being in contact, the right side of the smaller object is in contact with the left side of the bigger object, and here the right side of the smaller object is in contact with the right side of the bigger object. So in going from here to here, the smaller object has moved one diameter of the larger object. So 1 to 3 is going to give you the diameter of the larger object, as is 2 to 4. Again, you have redundancy built into the system, and you should be able to measure it. Knowing the time, knowing the velocity, you should be able to measure the diameters of these things. So that's really what it's about, trying to measure the diameter of the smaller object, Charon, and trying to measure the diameter of the bigger object, Pluto, and reporting those things out. So there's a worksheet here. As always, I don't care if you write on this worksheet or don't write on this worksheet, or you give me a sheet of paper that you turn into a PDF. That's what you're going to do with all of these things, is turn this into a PDF and upload it. I don't care how you go about doing that. And so but I want all that information in there. And then when you're done, I would like you to answer the discussion questions except for question 3. So answer 1, 2, 4, and 5 of the discussion questions. And so in this, show your work to do these calculations. I want to see your work to do these calculations. I want to see the data that would go in this sheet right here. If you use this sheet, you can probably show your work all down here at the bottom. This is a one-pager where you can show the work that you're doing, and then answer questions 1, 2, 4 and 5 of the discussion questions at the end of the lab, and that's what you got. That's what we got for the Pluto-Charon portion of this lab. Both of these labs, the exercise 18 and exercise 21 for the week of October 12th, are relatively short labs. So you should be able to get both of these labs done in under 3 hours of work and get the write-up basically done in under 3 hours with this. So that's what we got. That's your introduction to these. Do let me know if you have any questions, and we will talk to you later.